Imagine watching a rocket ship blast off toward a black hole. Nearing the event horizon, you'd expect gravity to accelerate it inward. Instead, from your perspective, the ship appears to be slowing down. As the ship zooms in, the light coming from it gets dimmer and redder. Because photons are emitted at discrete intervals, there is eventually a last photon emitted outside the horizon, and the image simply fades from view. At the very instant it should cross the point of no return, it appears to stop, frozen in time. From the outside, you can never actually see an object enter a black hole. This creates a gap between what we see and what we know must be happening. While the ship seems suspended forever at the threshold, the math of general relativity suggests a much more violent reality is unfolding. In the 1600s, Isaac Newton struggled with the mechanics of his own theory. He could calculate the orbits of the moon and planets, but he found the idea of action at a distance, one body acting on another, through a vacuum without any mediation to be an absurdity. It took over 200 years for Albert Einstein to figure out how gravity is mediated. He realized that mass curves space-time in its immediate vicinity, and the Earth orbits the Sun because it is passing through that curved geometry. Describing this curvature required the Einstein field equations, a family of coupled differential equations so complex that Einstein himself spent a decade working to formulate them, and he doubted an exact solution could ever be found. The first solution came from the Eastern Front of World War I. While calculating artillery trajectories for the German army, astrophysicist Karl Schwarzschild turned his attention to Einstein's new equations. Schwarzschild simplified the problem by imagining an eternal, static universe containing nothing but a single, non-rotating point mass. This solution describes how space-time curves around a mass, but the math breaks down in two specific spots, at the center and at a special distance known as the Schwarzschild radius, where the equation is divided by zero and blows up to infinity. These singularities implied the existence of a dark object so dense that even light could not escape it. At the time, most scientists, including Einstein, believed these were just mathematical errors that couldn't possibly exist in nature. For a star, life is a balancing act. The inward pull of gravity is held in check by the outward radiation pressure created by nuclear fusion. But when a star runs out of fuel, that outward pressure drops. Astronomers discovered that degeneracy pressure from wiggling electrons could stop a star from collapsing, leaving behind a dense white dwarf. But 19-year-old Subramanian Chandrasekhar realized this pressure has a limit. If a star is heavy enough, gravity will always win. The discovery was met with disbelief. Arthur Eddington, one of the most revered scientists of the time, publicly blasted the idea, arguing that a law of nature must exist to prevent a star from behaving in such an absurd way. The final blow to that skepticism came in the late 1930s. Robert Oppenheimer and his colleagues showed that for the heavier stars, there is nothing left to save them, and the contraction continues indefinitely until a black hole is formed. Physicists could no longer ignore Schwarzschild's math. The universe had a clear physical mechanism for creating the very objects Einstein thought were impossible. Oppenheimer also provided a solution to the observer's paradox. He realized that while time appears to freeze to someone watching from the outside, an astronaut actually crossing the event horizon wouldn't notice anything unusual at all. The singularity at the event horizon was actually just a result of a poor choice of coordinates. It is similar to how a Mercator projection distorts the size of Antarctica to fit a 3D globe onto a 2D map. The distortion is in the map, not the territory. You can visualize this by imagining space flowing toward the black hole like a waterfall. Outside the horizon, light can still swim against the current, but inside, space falls faster than the speed of light, carrying everything toward the center. To understand the full geometry, physicists use a Penrose diagram, which maps the infinite past, distance, and future onto a single plane. Here, light rays always travel at 45 degrees, making it easy to see that once you cross the horizon, Your only possible future is the singularity, but relativity doesn't dictate which way time flows. Mathematically, you can flip any solution to get its time reverse, revealing a region where things are expelled outward, but can never enter a white hole. When these maps are extended to their limits, they reveal even more. In the math for a rotating black hole, the singularity moves aside, opening a path through the center that leads to an entirely new universe parallel to our own. By correcting a coordinate error, mathematicians inadvertently discovered that Einstein's equations describe a vast, portal-connected multiverse. This leaves us with a choice. We have to decide if these white holes and parallel universes are real physical places, or if they are just ghosts in the machine of the mathematics. The primary issue is that these diagrams describe eternal black holes. They assume the black hole has existed forever in a completely empty universe, ignoring how a real black hole actually forms from a collapsing star. There is also the problem of the inner horizon. Inside a rotating black hole, infinite time is compressed into a tiny space. To an immortal astronaut looking back, the entire future of the universe would appear to pile up along that edge, creating an infinite flux of energy that triggers a new singularity. This effectively seals off the gateway, preventing anyone from ever reaching the ring singularity or the universes beyond it. Even the interstellar highways of science fiction have a catch. To keep a wormhole stable enough to travel through would require exotic matter with a negative energy density, something that violates our current understanding of the laws of physics. Mathematics is a canvas for exploring what the universe is capable of, but the unyielding properties of matter dictate what is actually possible. White holes and parallel universes may be allowed by the equations, but the physical laws of our reality appear to keep them firmly out of reach.